I told you that we'd be taking a break from Fourier, which is what we're going to do for the next couple weeks. In fact, we're going to talk about material that's not in the textbook. It's not usually taught in this course, but it's very fun. We teach it in this one over the years, and I think most people like this material. And you'll see how it differs in a moment as I get into it. You can read on this material in Kulkarni's notes that are on the website. Okay, I just listed on there, today I listed on the schedule which chapters are related to this, and you'll probably find that useful to go look at that. So, just a moment. So we're talking about this topic of going from an analog signal to a digital signal, and part of that is what we discussed last time. So this process of going between these involves both sampling, which was our topic last lecture, and quantization. Okay? Because on this side we have generally continuous time and a domain that's any real number. Right? And then in the digital domain, we need to be in some finite space, right? So we can record this digitally. All right. Now, what's actually done, I'll give you just a word on the actual implementation and how it differs a little bit from the way we'll think of it conceptually. So the implementation is something like this. You have a wire or some input node that has your signal x of t. You first do the low-pass filter. That's for anti-aliasing. Okay, so in here you had something like this, and out here you get something a little smoother. Okay, then it goes into what's referred to as a ADC, an analog to digital converter. Right, and out of here comes some bits. It's compared the input to different levels. So I'll just say you have something like this. And then you have a sample and hold. So you have something that has a clock, and this brings it to discrete time. Clock comes in here. And this then gets written to memory. And so only at the clock ticks are you carrying what the comparators told you at the analog to digital converter. Okay, this memory, it might be some big memory if you're just recording video or audio or something. Or it may be if this is some real-time processor. So it could be that you're capturing a signal just to process it and then reproduce the modified version in continuous time again, an analog signal. And in that case, what you would have is this would be a relatively small memory because you're not just recording the entire, song or whatever. It's just enough memory. It would be called a buffer. So just enough memory that you can do your processing on it. And it would just reuse this memory over and over as you're using the real-time processor. Okay. Now conceptually, and this is what we're going to care more about, it's nice to think about this as if first you did a sampling, the sampling from continuous time to discrete time. It doesn't really make a difference in, we can think of this conceptually as doing the following. So again, we have our low-pass filter, and this is anti-aliasing. Same reason as before. This is to remove the aliasing effect. Okay, we have our sampler here, which is just inside this. This is just a multiplication with a impulse I should write that box bigger. An impulse train. So that's what this box does. So again, in here we had something that had high frequencies. We filtered it out. And now we have what we were looking at last time. We have samples that are represented with these delta functions. And then we feed it into a quantizer. And out comes a digital representation of the magnitude of each of those samples. So something like these each would represent numbers having to do with the samples at the input. Okay. Now, the reason this is a nice way to view what's going on is that to this point, no information is lost. Well, if the signal is band limited. Or at least if it wasn't band limited, we understand very well what information was lost. All the information loss happened here in the low-pass filter, because we now know that we can recover from these samples this signal, right? So there's no information lost here in the sampler. But here in the quantization, we lose information that we can't get back. Okay. Let me draw and picture what we mean by quantization here. So we'll do a 2-bit quantization. Of course, with 2 bits, there are 4 quantization points, because there are 4 combinations of 2 bits, right? So here's what we mean. Suppose you have some signal like this. I'll draw a little bit different. Okay. And you have, now the quantization is in the range. Okay, so we have 4 quantization points, let's say. There's 1. There's 1. There's 1. Oh, they're not very straight, but okay. So here on the right, I'll represent the bit sequences, the 2-bit sequences that will represent each of these quantization points. Okay, so using 2 bits, we can record 4 different numbers, right? We can pick them to be arbitrarily, whatever values we want them to correspond to. And so what we're doing is this. We're saying, first, our continuous time signal, let's assume it's band limited already. Okay. Sampling of it is converting this to just a sequence of numbers, and I'll draw those as delta functions. So we take samples at certain points, like this point. Okay, so our sampling process just replaces the black line with these green delta functions. And if it was band limited, we can recover. But then the quantization is going to go through and say, okay, we're throwing away everything except we're going to round these to the nearest quantization point. So these red dots would be the quantized version. I'll suppose that rounds here, down. Okay, so our digital signal now is that sequence of points. So we would write it as a sequence of bits if we wanted. We would say it's 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, and there's some bits that represent our signal, right? I can put commas here so you can see how I did that. Okay, so there we go. We've gone from analog to digital, something we can work with in memory. Okay, obviously, once we have only this, we lost something. We don't know exactly what came in, and we can talk about an error signal. So let's let x hat of n be the reconstructed signal, which is the red dots there. Okay, that's x hat of n. It's our estimate of x. We no longer have x once we've done this quantization. So we can say okay, then we have an error signal. It's a sequence of n, and it is the difference between what actually the actual sample points minus their quantized version. Okay, so in other words, the error would be, and for this particular signal, we could say the error of n is a signal like this. That. Oh, they're all up. Yeah. Oh, there we go. Here's one that goes down. You see what I've done here is I've just taken this difference between the actual sample and the quantized version, and I've just drawn it below. Okay, so the error is what you would have to add to your reconstruction to get back the true original signal. All right. What we'd like to do is make this error very small. Okay. So let's talk about what this means in practice, because so far you've done things related to sampling, and when we work in MATLAB, we have quantized numbers, but you don't think about it necessarily. Seems like you have any number you want as the values of your signal, right? Because the quantization is actually pretty fine. Let's look at CD audio. So CD audio has a sample rate of 44.1 kilohertz. Has 2 channels, generally, for stereo sound. And it uses, let's say, 16-bit quantization. You can use more than that. I'll say, or something like 20 or 24. You can go; those are pretty standard. But 16 is supposed to be sufficient for CD. Okay. So what does this mean? Well, first of all, let's just why is this sample rate used? twice the highest frequency, our ears don't hear above 20 kilohertz. So if we filter all that garbage out up there, then we sample like this, give ourselves a little bit of room for imperfect low-pass filters and so forth. Then we get, then we don't lose anything audible by doing this sample rate. Okay. However, we do lose by quantizing. So there's some what we will call noise. So this error here, we will often call this noise. Of course, noise, you think of noise in a room or noise, background noise on a wire or something. Well, this is quantization noise. We produced the noise because we had to, right? Okay, so 16 bits actually gives you a lot of quantization levels. So that means 2 to the 16 equals what, 65, yeah, right here. That many quantization points. Okay, I drew a picture of 2 bits of 4 quantization points up here, right? You actually have 65,000 quantization points in CD audio, even if you're just using 16 bits. So maybe that seems like way more than enough. The error is going to be very small, okay? And we won't hear it, hopefully. Actually, CD is designed to not be audible. So there's some amount of noise that you're hearing, that biologically you can tolerate, that you don't even notice the difference. And if you put this to tests and ask people to tell the difference, they generally can't hear that level of noise, and that's why that's considered sufficient. However, we can do another calculation. Let's see how many bits this uses. How much data has to be stored. So we have this many samples per second times 2 times 16 bits per sample, right? That gives us that many bits per second over 1 million. Okay, let's just do a little conversion. That's going to be, if we divide by 8, here's how many bytes per second. And let's just look at per minute now. So it's 10 million. Bytes per minute. Okay, so basically we've got the bottom line here is that we're using about 10 megabytes per minute to store this that we just said. And this is this doesn't count the little bit of overhead in the protocol. It also doesn't, it's not even the highest quality. Right? By that I mean we could have gone to more quantization bits. Right? Yes?
I've seen like levels of CD audio where they change, like they claim it's higher quality. Is that
okay?
Is that higher? And I've seen higher sampling rates as well.
Mm-hmm.
So is that
so
make a difference?
You actually can gain something by going to higher sample rates. It kind of becomes, it effectively is like having finer quantization. I mean, ultimately, if you had no quantization, there's nothing to gain by going to higher sample rate. But because we're limited in the quantization, you can trade off rather than, it can be difficult to build higher resolution analog to digital converters, and sometimes the electronics of going to a higher sample rate is better, and you can show that that can be equivalent, basically. So going to high sample rates is sometimes used. Yeah?
So if we're looking at file formats like FLAC or AMAT that are fully lossless,
Mm-hmm.
do they just not quantize at all? Or is there some, or do they quantize to the point where you should be able to distinguish?
As far as I know, those are lossless from this starting point. So from a CD quality, they lose no more information. Because what we're going to have is, if you look at this, you say, this is kind of too many bits. I mean, you could imagine doing more, but a breakthrough happened when you guys were probably about 5 years old or something, back in the 90s. There was a major breakthrough that you could store audio with about 1/10 the size, and most people cannot hear the difference. What was that breakthrough? MP3, right? And that made a huge difference because if you wanted to use the internet to move music, then it really matters decreasing the file size by a factor of 10, right? And so what we'll talk about in this section, and you'll have a lab dealing with MP3, but what we'll talk about is this idea of, can you reduce this trade-off between quantization and noise, and can we reduce the amount of bits, that's called compression, without maybe noticeably affecting the sound. Now, MP3, it was just mentioned that there are lossless compression schemes. MP3 is lossy. So if you compress with MP3 and you compare the sound to the original sound, you will find they're not the same. It's designed to be not audible, not noticeable. Okay, so again, you can play tests of MP3s versus, let's say, CD quality or original sounds or whatever. You can play tests between these, and most people cannot tell the difference at all, even though it's very different. I mean, much less information is actually saved in the MP3. So it's done in a clever way, and that's known as compression. Now, what was mentioned is, and you mentioned FLAC. That's one of these. I believe that it's lossless only from the starting point of CD. So something's always lost in the first digital recording. But then they try to compress this in a way where the reconstruction would be exactly the same as the CD reconstruction. Okay. So to understand quantization, what we're going to need is some probability. So I'm going to take the next portion of this lecture to give a probability primer. Now, some of you have already studied probability. Most of you will study it. And this is not a replacement of anything you will study in depth, because it's actually a fascinating topic. I think many of you will find it's one of your favorite things to think about. But we should learn a little bit of the basics here, so we can just talk about some simple concepts. So let's start by saying that, of course, we're dealing with randomness. Let's say X is a random object. And, for example, it represents whether, let's say X represents whether a particular sports team, whether Florida is going to win their NCAA game this week, right? They're still in it, right? Okay. A team wins a game. Okay, so we'll say it's random because we don't know what's going to happen. It could take on several different values. So X is, in the end, once it's over, we're going to see that either it was a win, loss, or let's just suppose we're in a setting where there could be a tie. Okay, so you could have a win, loss, or a tie. And when we say it's random, first of all, we don't necessarily mean that everything's equally likely. I think that's one common misconception, is to say that random means sort of fully random. You have no information about it. That's not what we mean. We mean that it's modeled with a distribution. So there's some distribution, probability that X equals win, and maybe, for example, I'll suppose I know the distribution, that this equals 70%. And the probability that X equals a loss is going to be, let's say, 20%. And probability that X is a tie is 10%. Okay, so the first rules of probability are that probabilities can't be negative and that they sum to 1. Okay. Okay, so there's our first rules. The next simple rule, especially if we're in a setting where there's only a finite number of outcomes, the next simple rule is that the probability of, let's say, X equals win or X equals loss when you have different outcomes, the probability of the union of them, of one of them happening, has to be the sum of the two. So has to be 70% plus 20% equals 90%. Okay, so very simple, intuitive rules of probability. Now we have something that we call a random variable. And that just means that, well, first of all, I should give a name to this. This here, we say, is the space of all outcomes, so we'll call it omega. Every outcome that x could take. Okay, and a random variable is just this random object where omega is the real numbers. So in other words, it's the normal type of variable we think of. The outcome of this random object is going to be a real number, and we call that a random variable. Now, it's useful to separate out random variables as discrete and continuous. Discrete has nothing to do with discrete time. Okay, it just means that the space omega is some subset of R that is countable. Think about a finite subset. Okay, so I should say it's in R. So x x I don't want to get into analysis. If you're not familiar with countable infinity, that's fine. When you think about an infinite set that's countable, think of all the integers. Okay. Okay. Now, if you have such a random variable where it's always going to equal, let's say, an integer, okay, then we can assign. Then we have something called a probability mass function. And this is just a concise way of expressing what all the probabilities are for this random variable. Okay, so we might call it P sub x to represent that this is the probability mass function for the variable x. And what it means is that the probability that x, the random variable x, in the end takes a specific value, little x. So here we use capital X and little x to mean different things. This is typical in probability. You often use the capital variable to be the random variable, the thing that we don't know what it's going to equal. And the little numbers are just regular variables. So probability that a random variable x takes a specific value, little x, is given by this function. Okay, so as an example, if you're given a probability mass function, now here's x on the axis. If you have a probability mass function that that's just the following function, okay, so suppose that you're told that the probability mass function that represents x's probability mass function is the following function that I've drawn out here. I could easily write this in formula as well. I could say P of x equals 1/2 if x equals 0, 1/4 if x equals 1 or 2, and 0 else. Okay, so there's the formula representation of this probability mass function. I also often like to just draw it as a picture. And what does this mean about x? Does anyone want to offer up their thoughts about what this means based on what we've said? I mean, what can you tell me what's the probability that x is greater than a half? 0? And why do you say that? Okay. Yes, 1/2. So, yes, exactly, 1/2, yes. So what's the probability that x is greater than 3? Then that's 0. Okay. So the way we should interpret this is saying that x will be a 0 with probably half. It'll be a 1 with probably a quarter, and a 2 with probably a quarter. It will never be anything other than those 3 numbers. Okay, so this is just a concise way to describe everything we know, to describe the entire distribution of x. Okay, so generally we would call this the distribution of the random variable expressed as a probability mass function. Yes? I know. The uppercase x is a variable that we don't know the value of. It will have, it's the random variable. It could, now the little x is just the dummy variable. I could have put a here and here.
So what's the subscript x?
That's just to represent that if some people leave that off, but then what if I have 2 random variables I'm talking about? I have an x and a y, and they each have their own probability mass function. If I call them both p, it gets confusing. So it's just a p sub x is just a name of a function. Yeah. It doesn't have to. It's not required to have anything to do with the x in the argument. So actually, what we can do, some people will prefer this, is put a different. I'll put a different dummy variable here. Yeah, I'll do a. And of course, the meaning is the same, right? Because that's just for all a, right? Yeah, and then this would be, yeah, this would be a over here. Although I'm not going to change that because that confuses me. Okay, so okay, so any discrete random variable, its distribution is fully expressed by this probability mass function. Okay. Now, for continuous random variables, it's a little bit different. Then we have what's called a probability density function. Most people use a different letter. I guess I will here. I prefer to call them both p, and just know implicitly if I'm talking about a density or a mass function, but I'll use f since that's sort of more standard. So you have some f sub x, let's say a. It's a probability density function. And here what we know is that for any set, let's say S, that's a subset of the reals, okay, then what we would say is the probability that x is in that subset equals the integral over that subset S. Okay, so if this is confusing you, it doesn't need to be confusing. We'll talk about, let's just look at some common subsets. Okay, so one example of a density function would be the following. The uniform distribution. And the uniform distribution, you can talk about that in the discrete sense and the continuous sense, but since we're doing continuous right now, we have, let's say that fx of a equals 1/2 for 0 less than or equal to a less than or equal to 2 and 0 else. Okay, again, I like to just draw the graph of the density function. So here's x this way. We've got 0 to 2. We have height 1/2. It's like a little rect that's not centered. Okay, and this is a uniform distribution. Uniform distribution can be over any set, and here it's over the set 0 to 2. Okay, so this is one example of a uniform distribution. Let's see. I will write the uniform from 0 to 2 equals this. Okay, it's a particular type of random variable. Now, what it means is that if I asked you what the probability is that x is greater than 3/4, what would the answer be? 5/8. Okay, and how did we get that? Well, we came up here and we said greater than 3/4 is the following. Here's 3/4. And we have this set over here that we're asking about. What's the probability that it's in this set? And we should just integrate the density. Okay, so there's a reason it's called a density. When it was a discrete random variable, it had little points of mass along the real axis where the probability was going to occur. And in the density case, there's no mass points. The mass is spread out equally. I mean, not equally, but the mass is spread out along the number line with some densities in different places. Okay, and again, we still want to count how much mass. The mass is equivalent to the probability, and we want to say how much mass is in the set of interest. Okay, the same thing we could have expressed up here. Let me equivalently say the probability for the. Let's go back to the discrete case for a minute and make a statement similar to continuous. The probability that x is in some set. Okay, instead of saying the probability that x equals a, I could say the probability that x is in a set S equals what? By our rules of probability, what should this equal? We should add up the probabilities of everything in that set. Right? Because we already said probabilities of disjoint events, they have to add. Okay? So now we see that actually these look very, very similar because we have a sum here for the discrete case and an integral here for the continuous case. There's a reason I couldn't say the first form of the statement for the discrete case. What would be the probability, using what we've explained here, for this example, the uniform distribution, what is the probability that x equals 1? 0. It's not a half. The function is half at 1. Probability is not a half. In fact, it is 0 because if you integrate an isolated point, you always get 0. So for continuous random variables, the probability that it equals any single value is always 0. Okay? Therefore, it would not be very informative for us to try to define the distribution by saying, what's the probability that it equals every possible value? Well, that would be 0 everywhere. We would still know nothing about the distribution. Okay, so this more general form is what we need to define the density function. That it's the integral, and we now have a point of comparison with the discrete. It's the sum. Okay. There are other types of random variables besides these cases. All right, for one thing, you can have a mixture of the two. You can have a random variable that has a positive probability of taking some points, but yet has a density for some other regions. Okay, but there are even more convoluted, there are even worse random variables than that. There are random variables that have distributions that are singularities. They can neither be described by a density nor a mass function. Okay, we won't worry about these intricacies. We'll just always assume the random variable is either discrete or continuous. All right. So we have some rules then. Let me write the rules. Any function, so p of x has to have some rules, right? That one is that it's not negative. And the other one is that it has to sum to 1. Okay, it's just kind of the rules of probability we laid out at the beginning. So any function that's non-negative and sums to 1 would be a valid probability mass function. All right? And the density is very similar. The rules for a density function, f, it also can't be negative. And the integral has to be 1. Okay. It's just saying the total probability is 1. Again, any function that satisfies these two things would be a valid probability density function. It would define a distribution for a random variable. Okay. So we have something that we call expected value. It's very simple. We write it this way. We say the expected value of any function we want of x. Okay. F is just an arbitrary function. See, that's what I don't like. I'll use g. I don't like that I used up f for the density there. All right. Okay, so any function g of x, we define the expected value. It's a number. It's no longer random. Okay, it's just a number that describes the distribution of x, and it's the following. It's the it's the sum over x of the distribution of x times that function g of x. It's that simple. Now I've written this. This is for discrete. For continuous, you would change it accordingly. So if it was a continuous random variable, it would instead be the integral. So this is what expected value means. Now people like to call this the mean sometimes, okay, of the distribution. So we can go and look at some of the, a particular expected value that we like is, particular expected value we care about is the expected value of just x itself. So it's just a special case of what I have up there, where g of x is just x, okay? And this we would write as, and I'm no longer going to write it twice for discrete and continuous. Just always know that continuous is an integral rather than a sum, okay? So this, of course, is the sum of p x of x times x. All right. Now, like I said, this is the mean of g of x, is what people might call that. And this here is just then the mean of x, right? Or we sometimes call this the first moment of the distribution. Okay. Now, let's try to figure out why. So some of you are no doubt familiar with expected value. Let's calculate the expected value of x for the distributions above. But then let's talk about what this means. Why did we take a random variable and extract this number from it? Is it meaningful at all? Okay. So the expected value, let's start here. The expected value of x for this distribution. Okay. Someone want to offer up the answer to that? What was that? I heard something. 3/4, yes. Okay, so this is 3/4. And we got that by simply saying expected value of x equals, it's the sum over all values of x. Here there are only 3, so I'll write out the sum explicitly. The probability times the value of x. All right, and that's 3/4. So what does that mean to us? Well, notice first of all that this expected value is a point that you can never equal, right? X will never equal 3/4. And yet we call it the expected value. Some people find that funny because we don't expect x to ever equal this value. Okay. What it really is a center of mass. These were mass points. And if you think about the physics center of mass, it's the same thing. We're saying center of mass is this green point. Something more important about it I'll mention in a minute, but let's go on and calculate the center of mass, or the expected value of x for this one. It's 1. And we got that by symmetry. You can see it's going to be 1, right? But we could also write it out and say, well, this will be here, expected value of x equals the integral. Now, it's this integral, right? But that's just the integral from 0 to 2. Take the 1/2 out front of x dx equals, here we go, equals 1, 4/4. Okay, so we could have calculated it out by formula, but we see again it's going to be this center of mass, right? It's going to be right here, center of mass of this distribution. That was easy to see by looking at it. Okay. Now, there's a more important reason. Well, there's several reasons to focus on expected value of a distribution, but one of them is where expected value materializes is in what's called the law of large numbers. And this says that if you see many different independent copies of x, okay, oops. And they each have the same distribution. They each have, say, a probability mass function or density function. It doesn't matter here. The same thing. So this is referred to in probability as IID, independent and identically distributed. Okay, so all of these things, they're exact copies of random variables, but they're going to take the same value. It's like flipping a coin over and over, except instead of a coin, it's something that takes on some arbitrary distribution, and you flip it over and over. Okay. Now, if you look at the sample average, okay, you take all the outcomes that you got, and you take the average of them. All right, so that could be written as a 1 over n. N is the length of the sequence. X I equals 1 to n. Okay, so this sample average, all right, is going to be random because each one of these is random. You don't know what it's going to be, but you do know that it's going to converge to the expected value of x. Okay, and this is what the law of large numbers says. Now, if you look into this further, you're going to see that you need a new definition for convergence when you have probability. There's different notions of convergence, but without worrying about that right now, you can understand what this means. It means that if you flip a coin, say you have a fair coin and you flip it, what's the expected value? Let's say heads is 1 and tails is 0. What's the expected value of a fair coin? It's a half. If you flip it over and over and you take the sample average of how many heads you saw, that's saying the fraction of the time that you saw heads. This is guaranteeing that as you do this enough times, it's going to converge to 50% of the times you saw heads. So this is the law of large numbers. This is where expected value comes in. And in fact, to be more general, I can take any function here, g of x xi, and that's going to converge to the expected value of g of x. Okay, doesn't have to be x itself. Okay, so that's something to just tuck away as what the expected value means. It means this is what would happen if you actually took many samples and took averages. Okay. We have some other moments we care about besides this first moment. Let's look at second moment. Look at the second moment here. We have, that means that's the expected value of x squared. Okay, we call that the second moment of a distribution, whereas the expected value of x was the first moment. Okay, now, why is this important? If we apply the law of large numbers, then we're going to get that if we have a sequence of numbers, so the law of large numbers says that the average of the square value of xi is going to converge to the second moment. Okay, I'm bringing this up on purpose because we've looked. Let's say x was some signal. It's been some discrete time signal. Okay, we've talked about this type of quantity before. What does this remind anyone of? Let's say limit as n goes to infinity. What? Energy, or power, because we've normalized by n. Okay, so this is the power of a signal. You see this sum, the average square value of a signal, that's its power, right? Normally we've talked about power for periodic things. This may not be periodic, it's random, but you can still talk about its power. It's the average of its square value. And here we see that that's going to converge to the second moment. So that might be one reason why we care about the second moment of a distribution. Okay, because it tells us the power, and so you'll see me referring to that. Another thing that, just for your curiosity, you're going to like to see is the variance. The variance of a distribution is the expected value of x. It's almost like the second moment, but you remove the mean first. Okay, so x minus its mean squared. Okay, and so you'll be familiar with this because when you take the square root of this, you get something known as the standard deviation. If for no other reason, you've probably encountered standard deviations in grade distributions. Okay, so this is the square root of the variance of x. In other words, it's the square root of that above equation. It's the RMS value, if you want to think about root mean square of the deviation from the mean. Okay, so that's what standard deviation is, and variance is very much related to the second moment. It's just that you removed the mean. So let's look at these again. Okay, so we could calculate the second moment of this, but more. I'll leave that exercise to you if you want. Let's calculate the variance. The variance, we've already calculated the mean, so the variance of this distribution then is variance of x equals, it's the expected deviation, square deviation from the mean, which is 3/4. So let's go through that. That's going to be, we have a 1/2 probability of being here, and that deviation from the mean is 3/4. Right, so 3/4 squared, okay, plus, and now it's 1/4 times, and this is going to be 1/4 squared, because that's the deviation of that next point, right, plus 1/4 probability of being 5/4 squared. Okay, and haven't worked this out yet. Does someone want to do this? We get 18 over 64 plus 1 over 64 plus 25. Is this correct? If I do a mistake, please correct me. 44 over 64. Does that look right? Okay. And we could take the square root of that if we want to know the standard deviation. Okay. Now, uniform is one I'm going to calculate because we'll actually tuck it away for future reference. So this uniform distribution okay, don't really have room for it, but I'll put it here. Calculate it right there. So the variance of x above equals, now it's going to be x minus 1 squared. So it's going to be, let's write out the formula. It's the integral from negative infinity to infinity of fx of x times x minus 1 squared. Okay. And we again can say that's 1/2 integral from 0 to 2 of x minus 1 squared. Of course, we can do a change of variables if we like. Okay, and this is going to be, well, whatever. We'll do all right. I'm going to do from negative 1 to 1 of x squared dx. If you don't like that step, go do a u substitution. And 1/6 of 2. So 2/6, right? Okay. I think this is correct. 2/6 for this distribution. Now, notice that uniform, I could have defined uniform on any interval. Okay. For the uniform of width 2, the variance was 2/6. It turns out that for a continuous random variable, if I stretch this distribution or shrink it, in other words, if I went to a uniform from 0 to 1, of course, the variance would change in a very predictable way. Okay, the variance would become 1/4. If I shrunk it by a size of 2, then the variance goes down by 2 squared, 1/4. Okay, so in general, for uniform, let's say from 0 on an interval from A to B, okay, then it's going to be the variance equals B minus A squared, okay, the width of that interval squared, over 12. You'll see that you could recalculate it. You can also check that matches up with our derivation here. Here, where the interval was 0 to 2, the B minus A squared would be 4. Plug in 4 here, you get 2/6. You get 1/3. Okay. So we know the variance of a uniform distribution. We're going to use that in a minute. Okay, so that's the probability primer. We'll move on now. We'll use some of this stuff. Okay, so to understand quantization, what we're going to want to do is assume some sort of random model for our signal. Okay, so we've already, let's say we already have a sampled signal. Okay, we're just at the point of quantizing, taking those sampled values and fixing them to some point. So suppose we have a distribution so we need to assume a distribution of our signal. So we have some discrete time signal now that we're going to quantize. We need to assume some distribution to talk about the error. Okay. Now, one simple thing so let's assume we know that it has some distribution. Here's the value of x. Let's say we know that it's distributed like this. Okay. What this means is, so this is this is f sub x. This is the density function for our signal. Now, first of all, before I move on, how should I interpret what this information I gave you? Because if we look back at the beginning of where we were talking about quantization, here, this axis is time, or n. Okay? But the distribution I gave you is not related to time anymore. The graph I just showed you with the distribution of our signal. It's related to the range, values that x takes, vertically. So maybe it would be more appropriate that I had drawn that picture vertical. Okay? Because x is going vertically. Its value goes vertically. It's hard for me to draw, to work in that direction, so we've sort of rotated x to be flat, because we're no longer talking about time. Okay, we're assuming we have a bunch of samples, and we're just looking at the distribution of the values the individual samples take. Okay. Does anyone, especially if you've done the lab this week, maybe you have some interpretation, like maybe you can explain what this is related to? This distribution, like if I give you if I tell you that this is the distribution, what does it mean to you? It means, okay, there's a command in MATLAB that you used on images. What? Hist. The histogram, right? The histogram tallied up the different values of every pixel in the image. It told you, and let's say this was bright and this was dark. And it said, you have this many up here that are bright, this many that are dark. So if this was the distribution for pixels in an image, this distribution says you have more towards 1 than you have towards -1, right? Of course, in an image, it would be from 0 to 1. There's no negative colors, I guess, in an image. But this distribution is just telling you that we have more, it's more likely that x is up here towards 1 than it is down towards -1. That's what it's telling us. Okay, so it's similar to the histogram function that you use to look at the color distribution in an image. If this was an audio signal, this is saying our audio signal is bounded between -1 and 1, okay, but it's for some reason skewed that most of the samples are up here towards 1. That would be a little bit strange for an audio signal. You'd expect it to be more centered around 0. This would have some sort of offset, right? Okay. So then when we quantize, what we're doing is we're dividing up into points, quantization points, like this. I'll use a different color. Okay. And then we're rounding x to the nearest ones. So, for example, we have these imaginary lines between the quantization points, and everything in here is going to get rounded to that quantization point. Okay, and we notice a couple of interesting things. One is, first, if we talk about uniform quantization, as I've drawn it, uniform quantization means that I have equal spacing between the quantization points. So there's a couple of, so notice that if I have a fine enough uniform quantization, okay, if these points are close enough together, then the error, okay, the error after quantizing here, let's say that the sample actually, I actually have a sample that has this value. Red's not going to show very well. Okay, I have a sample that actually has that value, and it gets quantized, gets moved to the quantization point. Then the error is exactly that difference there. That's the quantization error. And we see that the quantization error, if the quantization is fine enough, is going to be roughly uniformly distributed. Okay, I'm not going to prove that here, but from the picture, hopefully you believe me, that the error will be if the quantization is fine enough. Now, that I say that because you can see by example that if you don't have very fine quantization, the error will not look exactly uniform. But as the quantization gets finer and finer, the error looks very, very uniform. So what's the range of this uniform distribution? Well, let's start by naming something here called the dynamic range. So let's call the whole width of this distribution is the dynamic range. Okay, now hardware, let's say hardware for producing sounds or for displaying images on a monitor. They have a dynamic range. It's part of the spec of the hardware. Okay, it says the speakers, you know, as you're producing sound, there's some number for the audio signal that would saturate the speaker. Okay, and any numbers above that are going to be meaningless. They'll be pushed down to that maximum number. In MATLAB, if you use the sound command, the dynamic range has to be between -1 and 1, just like I've drawn it here. Okay, if you feed it a signal, if you say sound, play a sound that has values outside of this range, they'll get rounded back into the range. Okay, because they use a dynamic range of -1 to 1. Same with images. If you use IM-show in MATLAB, or you send a signal to a monitor to display some images, there's a dynamic range how bright each pixel can get. It's usually going to be between 0 and some value. Okay, so we'll take that dynamic range and say, now if I use a certain number of quantization points, then the error is going to be the magnitude of the error is going to be less than or equal to the dynamic range, I'll say dr, all right, over 2, and over the number of quantization points. Okay, you see this? That's a bound on the error. And we can say that that's going to be the dynamic range over 2 times 2 to the number of bits used. Okay. So what we can do now is we can calculate the power of this noise with this assumption that the error is uniform over this range. We have a bound on the error, and we also know that it's uniformly distributed. Therefore, power of, this is the noise power, right, of quantization noise. What we want now is to use our formula for the uniform distribution. We want to take the variance. Right? So it's going to be, now here's our formula. We have a B minus A. In this case, it's the B minus A is exactly the dynamic range. Right? No, it's not. B minus A is this minus its negative, right? Because the error is bounded to be less than this and greater than the negative of this. Right? So it's going to be dr over 2 to the b, okay, squared over 12. So that's the noise power. All right. So that's a very simple calculation based on uniform quantization. Okay. You'll do a calculation with this in your problem set. That's why I worked it out here. All right. Yes, it's the power of the error, which I'm calling quantization noise. Yep, exactly. Okay. So we could calculate for CD audio, how much power is there in the signal. Now, you're going to want to compare it to the power of the noise with the power of the signal. That's what's going to be relevant, the signal to noise ratio. Anyway, I want to also mention that there's another, this isn't the only way we could do quantization, right? Can anyone suggest an improved use of this many quantization points here? Yes? Yes. Absolutely. Absolutely. So you mentioned that over here there's more, our signal is concentrated over here, so we should be using more of our resources, our quantization points over here. If we did non-uniform quantization, we would put more here and less over here, and we would end up with a lower noise power. Okay, so we have an easy way to calculate the noise power here. In that case, you would have to do a more complex calculation, but you would get a better noise power. In fact, you can come up with an optimization problem that says, place these points optimally to get the lowest power. And there's an iterative algorithm for doing that. Okay. There's another thing, and this is going to lead into our next topic, which is going to be about how to actually do compression in a clever way beyond what we've seen here, and that is that I mentioned, so the way I've represented quantization is that each quantization point is represented by a sequence of the same length. Okay? So 2-bit quantization meant you have 4 possible 2-bit sequences, 4 quantization points. However, we're going to find something very interesting, that if we use a different number of bits to describe the different quantization points, then we can actually get away with a better savings if we do it smartly. Okay? So suppose we did uniform quantization here, but for example, we use fewer bits where we expect the signal to be most often, and we use more bits in the rest of the space. Okay? Well, I don't mean more quantization points. Keep the quantization points the same, but actually use the shorter sequences to describe the ones that occur most often so that we don't have to write as many bits. Okay. There's a clever way to do this, and that leads into our next topic. I'm wondering, I don't think I have time to introduce it, so we'll just do it next time. All right, any questions about this? We have a few minutes. So let me see if I left out anything about the quantization portion. So let me just kind of explain how what we do next time. We're going to start into a topic that will seem completely unrelated, and the only connection will be, we'll be assuming that now we have some quantized signal that's now discrete, right? And we want to know, what's the best way of storing this in memory, all right, using the least number of bits. So the whole description I've given so far sort of assumes that you're not going to do anything really clever in the way you represent these quantization points. You're just going to assign them equal length sequences and store them in memory. We're going to see some really nice mathematics I think you'll enjoy that show the optimal way to store this in memory, actually. Okay, lossless compression.